Okay, so we're recording right now. So these are the sections in chapter 26. Okay, sections of chapter 26. Sections of chapter 26. Okay, do you see my screen here, Vanessa? I'm moving up and down here. Yeah. Okay, good. Thank you. So we already covered index of a fraction. We covered Snell's law. Okay, don't forget the index of a fraction is a property of materials, is an optical property. Index of a fraction, a very good way of, in case you still don't understand what the index of a fraction is, index of a fraction is also called optical density. Okay, index of a fraction of a material, right? Of a material is also called optical density. The denser the material, the denser a material is optically, the denser optically a material is, right? The more difficult for the light to propagate. Optical density. Okay, so the more optically denser a material is, the more optically denser a material is, okay? The more difficult for light to propagate along it. Okay, so for this reason, the higher the refractive index, the higher the refractive index of a material is, comma, the slower the light propagates. The more optically dense a material is, okay, the more difficult for light to propagate along through it, right? Through it. For this reason, the slower light propagates. Remember the definition, right, of refractive index, or let's say the definition of optical density is C divided by V, right? So here you go. We're gonna here write it in terms of V. Here you go. V goes to the left side. And goes to the right side. Okay. The higher the index of refraction, the slower is the propagation of light. Then the definition of optical density. Then the definition of optical density. Okay. And Snell's law. It's not exactly a law. I'm going to put it between quotes. I'm going to put it here between quotes as well. Which is Snell's law, which is a consequence of the least of the principle of least time is spelled out as follows. Spelled as follows. And you go okay. Refractive index of the medium number 1, right? times the sine of the angle of incidence is equal to the refractive index of the medium number 2 times the sine of the angle of refraction. And that what we have right in here. Okay, theta I is incidence, theta R prime is refraction, angle of refraction. And again, the angle of refraction is measured with respect to the normal between the two media. Okay, so very important here. The following always happens. The following always happen. 1. When light goes from one medium of lower refractive index to another medium of higher refractive index, okay, the angle of refraction ends up being less than the angle of incidence. Okay? And that's a consequence of this formula here. We can analyze this formula. Okay, and I'm gonna do it here before this consequence, okay? You know, N1, I'm gonna put it higher, lower, one medium. Let's see, when light goes from one medium of lower refractive index to another medium of higher refractive index. Okay, I'm going to write it here. N1, right, is less than N2. Okay. I'm going to write it down. The above formula implies the following. I'm going to change it here. Implies the following. 1. When light goes from one medium of lower refractive index to another medium of higher refractive index, okay, theta of refraction is going to be always the following. Is always true. The following relation is always very important, always true. Okay. And we can have the opposite too. When light goes from one medium of higher refractive index to another medium of lower refractive index, and then we're going to invert. The following relation will be always true as well. And even better is, you know, it's going to be more like that. Oh, and here too, right? Less or equal and greater or equal, right? Less or equal and greater than equal. Very important. We have this equality as well. And that's the illustration here that we have. Here you go. The light ray from the source is incident at this interface, and it is going from a medium of lower optical density to another medium of higher optical density. The light ray is bent towards the normal. And by the way, I have an actual picture in my website that you can see illustrating that in real life. Okay, this is not, let's go there. Science sensors tech.com. Let's go here. Okay, one more student coming. Let's take a look. My website, you can look at that. You know, if you want to check, for instance, my website. I'm going to put it here. Check, for instance, my website. with actual pictures that illustrate the above. ScienceSensorStack.com. And going back here, where is it located? It is polarimeter waveguide kits. Here you go. Waveguide kits. And here you go. Here's my laser pen. My laser pen, by the way, is right here in my hand. Okay? It's the same one that's pictured in there. Let's show you it again. Effects. Okay, right in here. Okay, now you can see my laser, right? It's the same one that you see there in the picture. And we get back to my background here. So what's happening here? Here's the laser being incident in a piece of plastic. The refractive index of this plastic is 1.5, around 1.5. Okay, so this is medium number one of lower. This is medium of lower optical density going towards a medium of higher optical density. The optical density of air is 1. The optical density of the plastic is 1.5. Note that this is the angle here, the angle of incidence. Okay, we cannot see the light ray, right? But you can picture it just by drawing a straight line from the laser to this point of incidence. You can see clearly that the light ray is bent towards the normal. Okay, you can see clearly. And when the light ray escapes the rod, this rod that you see right here, what's happening? Instead of following this straight line here, it's bent away, right? So the theta of refraction from a medium of higher refractive index to a medium of lower refractive index, the angle of refraction is greater than the angle of incidence. It's greater than the angle of incidence. Okay, so that's the real life picture. And you can also do that at home, play a little bit like that at home. If you buy a laser pen like this one, and a piece of plastic, can even be water. You can do that with water as well. Okay. And note, see that the light ray is very strong here, right? And then it fades away little by little. See that? Why is it fading away? Okay, it is fading away because part of the energy of this light ray is escaping this rod. Okay, that's why you have this light ray right here associated with this reflection. Same thing here, look. Light is refracted, but light is also reflected, right, at the interface. We have both reflection and refraction. Refract towards here, and then goes towards the interface of the medium and refracts back towards the air. But some of it is reflected, and everything else is repeated, okay? Refracts away and reflects. So the intensity of the light ray is decreasing because light is escaping this, not the rod, but this bar, this plastic bar. Okay? Plastic bar. Okay, and let's see, I'm gonna give you the exact right in here. That will be the better link. Okay, side illuminate optical fiber devices, waveguide kits. Okay, you can look at there, and that's where we get to the point where we can start talking about another important effect, right? Here you go. Here's the case of angle of incidence at the medium of higher refractive index, right? And light escaping towards the medium of lower refractive index. This type of effect that you see here, okay, this one specifically, right, going from a medium of higher refractive index to a medium of lower refractive index, has a very important consequence. I'm going to show it right in here. So let's say you are underwater, okay, and you have a laser or a source, a light source, just like my laser pen, right? If you go ahead and shine this laser at the interface between water and air, you already know that the light ray is going to be bent away from the normal, higher to lower. Okay? Then we're going to continue this experiment. Here you go. Here I will call N1, right? And here I call N2. Second medium has a refractive index lower than the first medium. Okay. Don't forget, we also have a reflection here, not just refraction, but we have reflection as well, okay? And I'm going to do that little by little, so you do not get overwhelmed, okay? Oh, what's going on here? Here we go. Okay. Well, the first thing that we do is the normal incidence. Under normal incidence, there is no refraction whatsoever. There is refraction, but there is no bending of the light. Okay. Some of the light refracts it, some of that reflects it. Some of that of the light is being reflected. Okay. And then we have the next step here, right? Here we go. I incline my laser. Okay. Some of that refracts away from the normal, but then we have an angle of reflection that's going to be equal to the angle of incidence. We keep on playing this game, okay? Until something happens, okay? I go ahead, make my angle steeper, okay? Note that the angle of refraction is greater than the angle of incidence, okay? Like that. Now, depending on the medium, there will be a point in which the angle of refraction of the light is going to be exactly 90 degrees, okay? And you're going to have this phenomenon in which we call total internal reflection. When the angle of refraction is 90 degrees, we have what we call total internal reflection. Okay, so the intensity of the light here is going to be the same as the intensity of the light here. Okay, so format shape. Okay, so beyond, and that has a very important practical application. That has very important practical application. Think about having light propagation along a medium without any loss in the intensity. At every reflection, light is 100% reflected. Okay, think about that. If we were to have something like that, take a look here, you wouldn't see the light fading away in this waveguide, right? And that's exactly what I have in the next picture. Okay, it comes to a point, look what's happening. That's, what you see right here is actually a patent of mine, okay? Nobody figured that out before. Although the concept is so simple, nobody thought that there would be practical applications for what you're seeing right here. Okay, so we have the light incident at this interface. It refracted, and because the angle is not steep enough, there will be some of the light escaping this wedge, this plastic wedge, okay? But then it comes to a point that no light escapes anymore. You can see that this intensity here is almost the same as the other two, right? Brighter here, less brighter, less brighter, less brighter, until it comes to a point. What's happening here? In which the light becomes the same intensity. Well, what exactly is happening here? Okay? What's happening here is very simple. Because of this wedge here in this wave, in this plastic, the angle of incidence for every reflection, the angle of incidence keep on increasing until the angle of incidence reaches a point where we have total internal reflection, the condition of total internal reflection, okay? That's what's happening here. You do not get this effect if you use a bar like that. A bar in which both sides are parallel to each other. And again, what you see right here is a patent of mine. Have been able to patent something like that. I discovered that, and now I'm making money out of this idea. Seems so simple, and yet has remained hidden from the scientific community for so long. Okay, I filed this patent back in 2009. Okay, until 2009, nobody knew about that. Actually, it's 2005. I discovered that in 2005. Okay, so let us document what I just told you. So here you go. The second case above has a very important consequence. Okay, depending on the angle of incidence of the light, okay, you may reach, no, depending, not depending, as you increase, right, as you increase the angle of incidence of the light, you will reach a point, in which the refracted, the angle of refraction, the angle of refraction is 90 degrees, will be 90 degrees, will be 90 degrees. At this point, we say that the angle, at this point, the angle of incidence, okay? The angle of incidence is given a special name. We call it, okay, let's go back here. Right in here, okay? Critical angle. We call it the critical angle. I'm going to abbreviate it by theta C. Abbreviate by theta C. Under this condition, we have the following. Go. Okay, we were using Snell's law here, right? For, for, for theta incident equal to theta critical, what does it imply? It implies that theta of refraction is equal to 90 degrees. Oops, I need to do it in another way. Oh no, here it's 90 degrees or pi over 2, right? Which is equal, pi, which is equal to pi over 2 radians. Okay. So now we can here write this equation. Okay, I'm going to replace theta incident by theta critical. I'm going to replace theta of refraction with 90 degrees. And then what do we get? We get the number 1 here, right? And we can solve this equation. And 2 over n1. Or the critical angle becomes the arc sine of n2 divided by n1. Okay, and we can even come up with some examples so you can have a feeling of how this equation works. Okay, so let's go to our Excel. Okay, let's see, P07 roster. That's what I want, right? And this one here, notes, and we're gonna need another one. Freeze panes. Okay. Going back to the equation again. N2 and N1, right? I'm gonna put here N1 and 2. I'm gonna make N1 fixed equal to 1. And then I'm gonna vary N2. Here you go. It's gonna be N1 is gonna let's see. No. N1 is the medium of higher index of refraction, right? So let's not forget N1 greater of N2. N1 greater than N2. Because it's the first, N1 stands for the first medium. That's what it stands for. Doesn't mean the medium with the lower refractive index, right? Not necessarily. It means the first medium, like that. So here, let's see. Let's start with 1.1, then we keep on increasing, 1.2, 1.2, 1.3, and so on. Okay. and N2 is going to be the air outside. And what I want to do here, I want to calculate the critical angle. Critical angle here. And how do we do that? A sine, right? Arc sine of, let's go back to our equation. N2 divided by N1. N2 divided by N1. And don't forget, this is in radians, right? This one is going to be in radians. The next one is going to be in degrees. Degrees. Even better, I'm going to put like that. A little O here. And then we superscript it. Okay. This one is not degrees, it's radians. Okay. And now we can convert that radians. We have a function, right? A radians function here in Excel. Very small critical angle. Something wrong here. Let's see what's going on. Yeah, there's something wrong here. Yeah, let's see. Let's take a look at the equation. This angle is too shallow. There's something wrong here. Yeah, this angle is too shallow. There's something wrong here. Let's see here. N1, let's see. N1 take the critical. N1 is going to be downstairs. Yeah, I don't see anything wrong here. But let's keep on going. Let's see what's happening here. Okay, the critical. The higher the refractive index, okay, the easier is for you to reach the critical angle, okay? So that's what it's showing here. Sign of incidence. That. Over N1. Let me see the over N1. Yeah. Okay, so that's, and now going back here to the notes. This one right here. Okay, at this angle, we have what we call the phenomenon, or at the critical angle, okay? At the critical angle, the phenomenon of total internal reflection. Total internal reflection means, which means that light is 100% reflected at the boundary. Okay? Of the boundary. This is very useful. This is very useful in telecommunications. This is very useful in telecommunications. Okay, because now we can propagate light along throughout very long lengths of material. Okay, and I'm going to show you here as well. I have my laser here. Laser. Right in here. Here you go. Here's for instance, an optical fiber. We call that an optical fiber. This thing has application to optical fiber, okay? The plastic here has a refractive index. Let me stop sharing. The plastic here, this is the plastic fiber. The plastic here has a higher refractive index than the surrounding medium, okay? And now instead of illuminating the plastic from the side, okay? Instead of illuminating the plastic from the side, I'm going to illuminate it at the very end, okay? And then what happens? Look at the tip of the fiber, okay? We have light propagating all the way down to the tip of the fiber, no matter what the bent angle here I make with the fiber. This light that you see right in here is undergoing total internal reflection inside this plastic. Okay? N1 greater than N2. So let's take a look at the book as well. And go total internal reflection, N1 greater than N2. This number here is always going to be less than 1, right? And we have this example here, water and air. We're getting 48 degrees here. Let's see if our calculations matches, right? What I got in there. I want to put 1.33 here, right? So here we go. They're getting 48. Yeah, 1.3. 0.85. Yeah, there's something I'm not getting. Let's see, radians. Oh, yeah, that's the equation that is wrong. Okay, I got it. Degrees. Okay, this part here is okay. This equation here is right. What is wrong is this one here. I put the radians instead of degrees. Nobody picked up on that, right? Oh, okay. Now you got it. Now you got it right. Now you got it right. I'm converting this into degrees. Okay. So as we increase the angle, right? As we increase the refractive index, the critical angle becomes smaller and smaller. You can see that this value here at 1.33 is equal to the value in your book, 48.8. Okay? It's equal to 48. I'm getting 48.75. Okay? Here they round it up to 48.8. Okay? And we can keep on going to higher and higher refractive indices. As the refractive index of the first medium increases, it becomes easier and easier to reach the critical angle. Okay? It becomes easier and easier to reach the critical angle. Don't forget, here is 65 degrees from the normal. Here is 56 degrees from the normal. So the angle becomes shallower and shallower. Okay, here too, it becomes shallower and shallower, right? When you have a refractive index of 2.0, right? We have a critical angle of 30 degrees or 0.52 radians. Okay. So practice that on your own, okay? It's not enough for you to just sit down and listen to that. It's important that you also do the same thing that I do here, practicing how this critical angle changes with the refractive index of the first medium. Let me get back my background here. Blur, here you go. Too ugly there in the back, right? So Let's also put, I'm gonna just for you, I'm gonna also put the velocity, okay, of the light in the medium, in the first medium and the second medium. First medium and the second medium. Kilometers per second. Kilometers per second. Okay. So how does it go? The equation for the velocity in the medium is 300,000 divided by the index of refraction. 300,000 divided by the index of refraction. Here is always going to be 300,000. Format cells, font, number, 1,000 separator. I'm going to use 1,000 separator here as well. Separator. Here you go. As we increase the refractive index, the speed of the light decreases, right? In the medium, the speed of the light in the medium. In water, the speed of the light is 225,000 kilometers per second. In that plastic, in this plastic fiber of mine, with a refractive index of 1.5, the speed of the light is 200,000 kilometers per second. And in the air, it's going to be 300,000 kilometers per second. Okay? So we are done with total internal reflection. By the way, the book mentions the applications of total internal reflection in the, oh, here you go. Here's a nice picture showing total internal reflection of this salamander. The guy took the picture at exactly the right angle near the surface of the water. Okay, some of the light from its body strike the air-water interface at angles greater than the critical angle and is reflected. So it behaves just like a mirror, okay? At the critical angle, you go, I can write that down here. At the critical angle, an optical material behaves just like a perfect mirror, okay? With 100% of light being reflected. Okay, you go. 48.8. 48.8 degrees. Right here. 48.8 degrees. Of light reflected. 100% of reflected light. Let's see if we have more. Total internal reflection. Okay, they're calculating the critical angle for different materials, right? For different refractive indexes. Okay. See that? Diamond 2.42 and to 1.00. Now, if the diamond is surrounded by water, the critical angle is going to be different. Okay? So what we have here, we use total internal reflection, not just in optical fiber, but we also use it with prisms, okay? Like in binoculars. You do not, if you have a prism just like that and placed here inside your binocular, you do not need to illuminize the surface of the prism for it to behave like a perfect mirror. All you have to do is to have an angle of incidence that exceeds the critical angle. And the critical angle we did, let's see, we did for 1.5, right? So let's take a look at the And this critical angle at 1.5 is 41 degrees. See that? 41 degrees. In this case of the book, the angle of incidence is 45 degrees, greater than the critical angle. Consequently, light is going to be totally internally reflected, and this prism is going to behave like a mirror, like a perfect mirror. Okay, that's another application of total internal reflection. Here you go, optical fibers. You already saw how a demonstration of my optical fiber, right? Right in here. If you go back to my website, I didn't take a picture of that. I should have done it and posted in my website. Unfortunately, I didn't that. But what do I have there? Yeah, here you go. I have the rod being illuminated from the side, right? What I didn't do, I should have done, was to illuminate the rod from the end face. Okay. If I get the right angle, you are going to we're going to have total internal reflection of this device. Okay. This plastic is a special type of plastic that's sold out there, and it has a special composition that allows you to visualize the path of the ray here inside. Okay. And going back here, what else do they have for this one? Here, that's how optical fibers are made up. You know, it has a core with a high refractive index. Most fibers, have two layers. The core with a high refractive index, a cladding with a lower refractive index. But you can also have the same effect just by removing this cladding, okay? Because the core we're going to have a higher, and the cladding, it's going to be what? Just the air around it. We can have exactly the same effect. Okay. Oh, and now we get into something here that might be of interest to you all, right? There is something called endoscopes or endoscopy. We use optical fibers as an element of an endoscope. And that's exactly what you're seeing right here. A doctor imaging the inside of the human body, not just the inside of the human body, but also in pipes, okay? In pipes that you cannot reach. You can put a pipe through, you can put an optical fiber through a pipe, an endoscope through a pipe, right? An endoscope has an optical fiber there, and image was what's in there. And then we do that for the human body as well. Since most of you are in the life sciences, right? That should be interesting for you to know that. Endoscopes, here you go. That's another application of endoscope. Okay, the doctor looking in the inside of the leg, arthroscopy surgery. Arthroscopy surgery is a small surgical instrument, several millimeters in diameter, is mounted at the end of an optical fiber cable. Okay, and a small surgical instrument. The surgeon can insert the instrument and cable into a joint, such as the knee, with only a tiny incision and minimal damage to the surrounding tissue. That's the importance of an endoscope. Consequently, recovery from the procedure is relatively rapid compared to recovery from traditional surgeries, in which you have to make a huge, not just a little hole, but a huge cut, right, in the leg or other places. Here you go. And that's what we have for 26.3. 942 right now. Let's go back to my notes here. Right here, right? Let me, total internal reflection. For now, we are going to skip polarization, right? I'm going to start with dispersion. Whatever is bold-faced here is the material that we are covering, right? Dispersion of light. What is dispersion of light? I'll come back to that. Okay, I'll come back to that. Let's talk about dispersion of light. It's very easy to understand dispersion of light. Dispersion of light. Materials with a given optical density exhibit dispersive, optical dispersive properties. Optical dispersive properties. Now the question is, what is dispersion? What is dispersion, right? Well, it's very simple. It's not, looks like a name that's very scary, right? But it's not that difficult to understand, okay? Dispersion is the property in which the refractive index of a given medium is a function of the wavelengths. Okay, that's what dispersion is. Okay, so if I say, okay, so in reality, okay, many optical materials do not have a constant refractive index. Okay, that's not many. All optical materials do not have a single refractive index value. Instead, the refractive index depends on the wavelengths of the light. Okay, can you remember that? That's what dispersion is all about. That's what dispersion is all about. We can go. There is a very nice catalog there. Let me shot glasses. There's a company called Shot Glasses, and they're very good because here you go. That's their website. You know, they produce all sorts of glasses of different refractive indexes. And those guys are so through that they have all sorts of measurements of the dispersion properties of their own glasses. Okay, here you go. Change book setting. Yes, I agree. Solutions, market, careers, our expertise, careers at shot. Let's see if I can get one of their catalogs here. Products and expertise must be here. I once was showing that to my students. Services, technical glass tubing, pharma consulting, training, expertise on special selection tool, product selector. What a shame, I can't find it. But let's take a look elsewhere, okay? Let's take a look. Markets and application products, solutions, magazine. Yeah, they have sustainability, document search, must be here. Safety. Let's see, maybe it's here. If I don't find it here, we move elsewhere, okay? Product certificate. Okay, optical property. Okay, I cannot find here on Shot website, but they do have a catalog. It's optical glass. Let's see, products variant, optical glass. Overview, applications, technical details. Let's see. Okay, let's see. Here, okay, that's the refractive index. Okay, yeah, see, here's a table of refractive index. a table, no, a graph, right? Showing all sorts of glasses. Here you go. Everything that you see here is one type of glass: LAF, LAK, BAK, PSK, FK, and so on. F. I bought glasses like this one here. This one, the F glass, I bought from them some time ago. And I used to work at NAD. Look at the refractive index range. It's anywhere between 1.45 all the way up to 2.0, almost 2.05. Okay. And they have N glasses, P glasses, and so on. But let's take a look at the, Schott has a catalog of the dispersive properties of their glasses, but I cannot find it right now. So let's go at Wikipedia, dispersion, optical dispersion, Wikipedia. Dispersion, right in here. So dispersion, prices, science and mathematics, dispersion point, physics, optics, this one here for light waves. Okay, so here you go. Here's a very nice picture of what happens to different colors in a glass. Okay, so what's happening here is the following: white light is incident in this glass, and because the refractive index of the glass depends on the wavelengths of the light, okay, you are going to have different angles of refraction for each wavelength. Red wavelength is going to have an angle of refraction. Orange is going to have another, yellow, green, blue, violet, and so on. Okay? And we can, let's see how the book must have a very good, okay. Yeah, here you go. Very good. That's a very good illustration here, right? So incident white light, which by the way is made up of every color that we can see. No, you can see that the violet light sees a refractive index that's higher than the refractive index of the red. Okay, so you can imagine your normal right in here. You can see that the violet is bending more than the red light. And what does it mean? It means that the refractive index for the violet light is higher than the refractive index for the red light. Okay? That's what it means. So the relation is more or less like that. It's an inverse proportion. Okay, inverse proportion with the wavelengths. So if we go back here, it's an approximate. Okay, I'm not gonna say that is a okay, the shorter the wavelengths, the higher the refractive index. I'm gonna put it like a proportionality. Okay. So if I right in here, I like this picture better. I like this picture better. Okay. So here you go. White light is made up of every color that you have out there. Okay, made up of every possible wavelength in the visible light: red, green, blue, yellow, and so on. Okay. When it is incident at the interface of air and glass, for instance, blue light and violet light are going to be bent more strongly than the other colors. Okay, so here we have blue, green, and red light, and then they exit at different angles as well. Okay, because the angle of incidence here is different from the angle of incidence here. Did you get the idea? Okay, that's what you have to know about dispersion. And 9:53 right now. Shot glass website. Oh yeah, here you go. I have the shot glass website reference. Here you go. Let's see if I can get that for you, so you can see the actual numbers for real glasses. Okay, it's I had recorded here in my notes of last year notes. Let's see if this one are safety. Let's see. Data sheet, optical glass, data sheet collection. Okay. Let's see if this one 4.1 megabytes. Let's see if this one has what I want. And then if it is what I have in mind, I will post there in my, here you go, shot, catalog, data sheets for different glass types. They call it FK, PK. Each of those are different type of glass. And then you have subclasses, right? F, SF, and so on. Okay. Here's the dispersion relation, dispersion formula, which is similar to what I told you, inversely proportional to the wavelengths. And they measure the refractive index of the different glasses at different wavelengths. Imagine the amount of work it is to do that, right? For this glass here that you see, they got the refractive index at these wavelengths. This wavelengths is in the infrared, infrared, all the way down to here is the infrared. All the way down to here is the infrared here, all right? Note that as the wavelength increases, right, the refractive index decreases, right? The refractive index decreases. Here you go. Is 1.52 at this wavelength, which is, by the way, in the ultraviolet. It keep on decreasing as the wavelength increases, okay? 51.8, 51.4, 50, see that? So that was the phenomenon of dispersion is all about. I will give you, I'll place, here you go. Look, for instance, at the dispersive measurements of different glasses, of different optical glasses in the shot glasses website. Here you go. That's the link that I was looking for. I couldn't find it. Wait a minute. No. It's not this one. Sorry. This is the link in my computer. Here you go. That's the one you want. Okay? That's the one you want. At this link, you can download data sheets, a data sheet containing the optical dispersive properties of different glasses. Okay. Here, right? Yeah. That's for FK, right? See you have 138 pages here in this document. FK, another, let's see. Yeah, that's the first class, FK5HTI. Now this other glass, NFK5, right? NFK51A. They have refractive index that are slightly different, 146,958. Let's see how different it is. 14658. 14658, right? 14618, right? Same wavelength. So because they are different, slightly different glasses, they're going to have slightly different refractive index at the same wavelengths. Okay. Wavelength 280, 152,409. Let's take a look. 15241, right? Right here, 41. And so on, okay? So there must be, I suspect that there must be like 65 different glasses here, optical glasses. The property, the data sheet of each glass, actually is more, right? Because each optical glass has a one-page data sheet. So we're talking about around 130 different optical glasses. That's what SCHOTT does. It's a very good company, you know. They are a German company, well-known company in the business. They have been around for, I believe, more than 100 years. And during the story goes that during the Second World War, they have factories set up there in Germany, and they knew that their factories are going to be bombed by the Allied troops. Okay, so what they did, they came up with a plan so they wouldn't lose their knowledge. Think about that, losing all this knowledge, even though they were working for Hitler, right? That wouldn't be good if we're going to lose all this expertise in the glass community. So their plan was to transfer many of their activities to Japan. That's the story that I heard in the community. Okay, here you go. And BK7, and they're still around today. They survived the World War, the Second World War. Okay, and again they're still around. 10 o'clock right now. You have it. Let's see. Let me save this one here. So we don't need to go spring 2024 SCHOTT optical glasses. SCHOTT optical glasses, okay? And we're gonna get here attendance. Any questions? That's going to be 1st of May. Okay, remember we had a holiday last week, right? It was the 24th. 24th holiday. Click and drag. Right here, today is May 5th.
Professor, do we have any more holidays or no?
Let me check. I don't think so. I don't, or do I, Louis? Let me check. If we have a holiday, it will be here in my schedule. Let's see. Today is 1st of May, right? We are writing here. Oh yeah, we do have Memorial Day. It's gonna be a Monday. Okay. And we are doing lenses too, right? We will continue with refraction next, lenses 3. It would be better call it refraction 1. Refraction 1. Let's call, that's first meeting on refraction, second meeting on refraction. Someone is trying to come in. Okay. Flashlight bulb. Okay, I don't need that. And then we're gonna have refraction again next time. It's not gonna be interference. Let's see if we have time, okay, to cover interference. Refraction would be the third one. That's going to be chapter 26. I'm not sure if we will be able to have time to do 27. I'm going to put a question mark here, but definitely is going to be, you're going to see relativity theory. Today, we will have this lab number 7, flashlight bulb, okay? And I want to take attendance. And Jacqueline, are you there? Okay, thank you, Jacqueline. Yorgo is here, right?
Here, yeah.
Thank you. Lizelle. I don't see Lizelle in my list. Paul Zapata. Okay. And Sky. No, wait a minute. Norberto. Norberto. No, Sky comes from, not yet. Norberto, are you there? Let's see. I don't see Norberto in my list. And Vanessa Mena.
Here.
Okay. And Sky. Now Sky's turn. Hello, Sky. I'm gonna put a star here on her name. And Ashley. Hello, Ashley. Just say you're there. Okay, I don't hear from Ashley. Next is Corina. Corina just joined us, right? Yeah, thank you, Corina. And we have 7. 7, okay. Good. 10:05. Let's go for our meeting. Meeting on our break. Break 10:05 a.m. to 10:20 a.m. Okay, and I see you in 15 minutes. Yeah. Hey, folks. I was talking with my microphone muted, right? So sorry here. So let's go back what so I spent all this time talking to my cell phone here. You're not listening, you're not hearing me, right? So I forgot to turn on my microphone in my video. Okay. So let's go back and repeat what I said, right? And I'm gonna also share the screen. Here are the sections we have covered so far: 1, 2, 3, 1, 2, 3, and 5. Okay, hopefully we're going to have time to get back to polarization, but the priority right now would be to start spherical lenses, not today, but next time that we meet, okay? Formation of images, the scene lens equation, okay? That's what I want to cover. I do not know if there will be time to cover the rest. Maybe human eye, okay? I'm not sure about the other one, okay? But I will cover as much as I can. And I want to get back to polarization too. Okay. And what else? Okay, I mentioned about the shot glass website, and you want to concentrate on those two parts of the website. Optical glass overview is an Excel table with all sorts of glasses and their refractive index and other optical properties. This is the collection of data sheet. What else? We have, oh yeah, I want to show you the book. The book has a table for the dispersion properties of a special type of glass that's called crown glass. Notice that the shot tables are far more detailed than this one, right? Here they come up with just a few wavelengths: 1, 2, 3, 4, 5, and 6. And what you have to remember about dispersion is that the refractive index goes with the inverse of the wavelengths. The shorter the wavelengths, the higher the refractive index. The longer the wavelengths, the lower the refractive index, okay? So that's what you have to know about the dispersion, okay? The refractive index is inversely proportional to the wavelength, okay? That's what you have to do. Give me a few minutes. There's something that I got to attend quickly, okay? Okay, I'm back. And the relation would be more or less like that. What you saw there in the shot glass website is not exactly like that, okay? But it ends up being the same. The general behavior ends up being the same. Okay, and we are done with our break. What else I want to show you? Remember that I told you that the correction of the lab reports are going to be provided in a PDF file, okay? I discovered that Excel is allowing me now to do that. When I start doing this type of correction, I was having a hard time converting that to the PDF file. At that time, it was when? It was back in 2015, 2016, okay? Almost 10 years ago. And then it looks like that Excel now is allowing me to convert those corrected files into PDF. And I hope I'll be able to continue saving it as a PDF file. All you have to do is to download it and double click, and you don't need to worry about folders anymore, right? Folders and HTML files. Okay, so in a way, that's a good news. Hopefully, Excel will continue providing this type of feature. And I'm going to upload your data. And let me see, let's see. We have a student that just by herself in the group, right? Is that Vanessa, right, Vanessa? Are you there, Vanessa? Let me see. I don't hear, I'm not hearing from you, Vanessa, but let's see here. Yeah, Vanessa has been doing the labs by herself because her. Sky, are you there, Sky? Yeah, I don't hear from Sky. So we have 1, 2, 3 students in group 1, just 1 student in group 2, and now we have 2 students in. Oh, okay, 1, 2, and 3 students in group 1. Only 1 student in group 2 and 2 students in group 3. Maybe Sky will show up here with us, right? Maybe 3 students, right? But let's go for our lab number 7. I'll get there. Our labs. Okay, I will. Okay, now copies. Okay, group number 1. I'm going to upload your spreadsheet. But first, let's make sure everything looks good here before I expose you to the data. Six, 4. That's good. This experiment is going to be very similar to that of the resistor, of the single resistor. That's good. Okay. Okay, good. So let's go group 1. Your data sheet for lab 7 is there, group 1. Group 2. Data sheet for group 2 is in there, and group 3. Okay. And I'm going to get the lab slides. Like right in here. Okay, and it's very, like I said, it's very similar to this lab is very similar to lab number. Trying to remember the number 764. Should be very similar to lab 4, with one important difference. Okay, here you go. It's very similar to this lab with a single resistor. Lab 7. Okay. And there's a very important difference here. Gosh, let me get my notes first. Light bulb. Light bulb. Okay, lab 7. Here you go. Whoops. Flashlight bulb, lab number 7. What you have to know. Okay, so far we have seen circuits that are made of ohmic elements only. Okay, ohmic elements. How do we define ohmic elements, right? Ohmic elements are elements that obey the Ohm's law. V equal to Ri. Resistors are ohmic elements. Resistors are ohmic elements. Is an ohmic element. An ohmic element. But then there are other types of elements. They don't behave like that. They do not behave like that. Okay. Another way of putting this equation would be like that. R equal to V divided by I. Okay. That's another way of putting that. There are other elements out there in electricity and electronics. We use them in electric circuit. They do not obey Ohm's law. They obey a more generic law that I'm going to write that down with here. Instead, they obey a more generic Ohm's. Instead of law, let's put it relation. It's not. I hate when when relation. Here you go. I hate when the scientists they start to call law something that are not law. Okay, and this error keep on propagating on the books for some reason. Just for convenience, I guess. I don't like it. Instead, they obey a more generic relation, which is given by. I'm gonna write that down here. Which is given by. Here you go. R, the resistance, okay, is equal to what? Delta V over delta I. Okay. Ohm's law is just a special case of this relation that you see right in here. Okay. And by the way, this resistance is going to be a function of V and I. Okay. In Ohm's law, the resistor is not a function of V and I, but the more generic relation is like that. It's just like that. One of these elements is the flashlight bulb. The flashlight bulb is it's not an LED. The flashlight bulb, I'm not talking about the LED, right? But I'm talking about, every time I forget the name of this type of light. What's the type of light that is attributed to Thomas Edison? Invention. There's a name, invention of light. Light bulb, there's a name for that. Incandescent. Oh, I always forget it. Incandescent. Okay, the flashlight bulb is an incandescent. One of them is the flashlight bulb, an incandescent. An incandescent. Incandescent light. Okay. Incandescent light source. I've just written here. I didn't even see. Okay. Because in this case, the resistance of the flashlight is not constant with V and I. Okay, it's not constant with V and I. So go ahead, download their respective, and you will appreciate that in this lab. Okay. So let's take a look at the list of equipment. List of equipment. Digital multimeter. Did you notice that we keep on using the digital multimeter over and over again? 2 black cables with banana termination, 2 red cables with banana termination, 2 alligators, alligator clips, 2 alligator clips. Okay. An electric resistor, ohmic element, anomic element, right? Anomic element. Anywhere between 30 and 100 ohms. Proto board. I didn't put the flashlight bulb here. What a shame. Flashlight bulb. Flashlight bulb, right? There you go. Power supply. And as they appear, I'm going to list them according to their appearance, right? So here you go. Here is my slide. Okay. Turn on the digital multimeter. Okay. Digital multimeter, DMM. That's the first device that appears in my. I'm going to close this one here. This appears here in my slide. You know, make sure you set the multimeter to measure resistance. Multimeters can be used to measure resistance, voltage, current, and some other things too, capacitance, depending on the multimeter, frequency of a given circuit, right? What else? We have the jacks there in our multimeter. I'm going to use the black banana termination to the black jack, right? So here you go. 2 black cables. This banana termination, we're using one of them. And then we are going to clamp the red alligator to the end. Clamp red alligator. Okay, to the other end, right? Other end of the red cable. So now we have the alligator right here. So we have this one. We talk about this one, right? And we can follow according to the simulation as well. Very soon I'm going to get there. So let's go there. Let's go there right now. PET. Here you go. PET simulator. PET simulations. I want that in English. Okay, that's okay. There might be a way to switch to English here. Ensino, pesquisa, simulação de iniciativa. Yeah, it's in Portuguese, unfortunately. How do I get? Okay, here you go. English? Maybe English? Yeah, now I have it in English. Moment. Ah, could not be found. What a shame. Ay, 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 ay. Okay, so let's start from scratch. You go. So it's slow today. Why is that? Physics. Physics. Okay, electricity, magnets and circuits, motion, sound waves. Okay, so here we go. We worked with that before. Do you remember that? And AC, we're not using AC circuit, we are using a DC circuit. Okay, direct current. Let's see if this one has what we want. Let's see if they have a flashlight bulb here. Okay, so here we go. Ohm's law. Introduction. Let's see this one here. Light bulb. Let's see fuse. Oh, they don't have a light bulb here. Oh yeah, they have a light bulb here. Okay. So how are we doing? We're gonna get our ammeter, right? Oh, we don't have an ammeter here, unfortunately. And measure the resistance. That's what we're going to do. Here you go. Clamp red alligator to the other end of the red cable. Black alligator to the other end of the black cable. Clamp the alligators to the two ends of the resistor. What are we doing here? We are measuring the resistance of the resistor that I provided you. Okay, where's the resistor here? Two red. Yeah, there's a missing device here, right? Two red cable banana, two alligator clips. Oh yeah, the resistor is here. Sorry. Okay. The first thing is to measure the resistance of the resistance value with the multimeter, of the resistor with the multimeter. That's the first thing that we're doing. I'm not going to illustrate in the simulation because they don't have a ohmmeter here. They have only a voltmeter and a ammeter. Okay. And that's where we get to the point where we have our first data sheet, first value, first measurement. Copies right in here. Right in here. Here you go. See that? The resistance of the resistor. The value is right in here. 81.12. There's a reason why we use this resistor here, right? And I'm gonna tell you very soon. So for this specific case, I measured the resistance of the resistor with the multimeter, and I got this value. Don't forget to put that with the proper number of significant figures and with the proper format as well. And then what else are you going to do? You're going to measure the resistance of the light bulb whenever it is disconnected from the circuit. When it is disconnected from the circuit, we call it that the light bulb is unloaded in its unloaded configuration. Every time that you measure the resistance of any device, it has to be by itself. Okay? You cannot measure their resistance whenever they're connected to a device, whenever they're connected to a power supply. Okay? Cannot be, see, the resistor cannot be connected to any circuit. Okay? The same thing here. The light bulb, when measuring here, when measuring the resistance, when measuring when measuring the resistance. When measuring the resistance of the resistor, it cannot be connected to any. It cannot be connected to any circuit. Okay, has to be unloaded resistor. Is the same thing for the light bulb. When measuring of the light bulb, when measuring the resistance of the light bulb, it cannot be connected to any circuit and unloaded the flashlight bulb is flashlight bulb. Unloaded flashlight bulb. Yeah. Unloaded. And then what you have to do next, after measuring those two resistances, then you can put your circuit together. Okay, connect the resistor and light bulb in series using the proto boards. So now we use the prototype boards. As we go along, as I introduce the element, I will both face that line, okay? And how do we do that? I'm going to do that in the resistor, right? Connected to the light bulb. Okay, here you go, let me cut that. Okay, notice that I connect a wire to one end of the resistor and a second wire to the other end of the resistor. The light bulb also have two ends, which are not apparent, okay? One end is the tip of the light bulb. That's one end. This black line that you see here is what? This black line that you see here, this black band that you see here, is actually a dielectric material that separates the tip of the light bulb from this other region here of the light bulb. So you can connect it to one end and connect to the side when you put together a circuit. Have you ever noticed that? Okay. I have, let me get a lamp that I have here. A real life lamp. Let's see if we get that. A real life. Here you go. Here's my lamp. Okay. Can you see? Where's my? Where's my? Oh, where is my? Can you see me, folks? I can't seem to find my picture here in my. Oh, okay, I found it. Okay, good. Here you go. Here is the model of a light bulb. Okay, an incandescent light bulb is exactly like what you see here. You have the tip here. That's one end of the light bulb. you have this band. In this case, this band is not black, it's white. They painted it white. And this band is a dielectric material that separates the tip from this body that you screw in the wall, right? So this is one end of your light bulb, and this is the other end of your light bulb. Okay? They are electrically insulated. This end is electrically insulated from this other end by this band that you see right here. This is a real life light bulb. Okay? And I want you to see that. Here, incandescent light bulb has also a filament here inside. Okay, the filament, one end of the filament is connected to the tip. The other end of the filament is connected to this other part of the lamp. Okay. And we measure the resistance value of the resistor. We measure the resistance value of the light bulb. And now we are going to get those two devices in the protoboard first. They're going to be connected in series, just like I connected in series there in the simulator. This is the symbol of the light bulb, okay? Is this filament here inside, incandescent light bulb, but then on the top of that, they have this circle around it. Every time that you see a circle around whatever, okay, it indicates that the device is a light source, okay? Make sense? Every time that you see this, the so-called aura, right? Aura of Jesus Christ, for instance, aura of the apostles of Jesus Christ. Okay, what that aura means in their head, that aura means that they are the light, okay? They produce the light. It's the symbol of the sun. It's the symbol of the sun in the sky. Not the Son of God, but the sun in the sky, okay? And every light source you're going to see is going to have this circle around the element, every light source. This is the first one that you're seeing right now. An LED also has this circle around it. Okay, and you're going to see it next to lab. So we connect those first, and then we're going to put together the power supply now. We're gonna get the power supply, here you go. We're gonna put the power supply in the circuit. Okay, this flashlight. Okay, this flashlight bulb is supposed to go right in here after the resistor in order of appearance. Okay. We're going to connect the power supply to the resistor number 1, the light bulb, and we're going to close the circuit. That's the symbol here. We can go to the simulation as well. Because my power supply is going to be my battery. And let's see how I want to follow according the positive would be facing the resistor. And we close the circuit. Oh, by the way, I want to put a switch right here. Okay, right here. Now we have it. We have the circuit. If I close the circuit, the electrons are going to flow in this direction. If I'm going to show the conventional direction of the current, it's going to be the other direction. So here you go. Here's the current passing through the resistor, passing through the light bulb. Notice that the light bulb is shining, right? And returning to the other side. Okay. That's the circuit that we have here. And what we're going to do next, we're going to use the multimeter to read the DC voltage in the circuit. Let's get connect the resistor and light bulb in series, the proto board, red cable to the red jack of the power supply or the battery, right? Clamp one end of the resistor with the alligator, click. The red cable, resistor is already connected in series to the light bulb in the proto board. Other end of the light bulb connected to the black jack of the power supply. So the black cable set DMM to read voltage. And in order, since we're setting the DMM to read voltage, we have to use the voltmeter. I'm gonna put this voltmeter here outside just to show that we're going to use it. Connect the DMM between the closer end of the resistor and the far end of the light bulb. Okay, so here you go. Closer end of the resistor, far end of the light bulb, can be either here or here. Okay, since this battery here is set to 9 volts, the voltmeter is reading 9 volts as well. Okay, I'm going to set the power supply to 10 volts, just like we did for the previous experiments. Okay, I gotta put another one here. Here you go. Connect the DMM between the ends, right? Set the power, and what does it look like in the? It looks like that. Here you go, the digital multimeter. One end closer to the positive end of the power supply, the other end on the indirect connection with the negative end of the power supply. This thing here is supposed to be here. Okay. Resistor, light bulb. Next, use most sensitive scale. We have to increase our voltage, right? Let's increase our voltage to 10 volts here. Okay, here you go. Now we have 10 volts, and then we are going to start our measurement now. Read the voltage in DMM. Go in here. Here you go. Voltage in the power supply, 10 volts. Read the voltage, the total voltage. Right now we are measuring the total voltage. Okay. And then what do we do next? Decrease to 8, 6, 4, 3, right? A little bit less than 3. Read the total voltage. It's going to be very similar to what we had before, with what this power supply is indicating. Okay. So repeat. No, not this one. Repeat step 10. Here you go. Invert polarity to get a negative value. And repeat steps 10 through 11. And what happens? Okay, we're inverting the polarity here, right? All the way up back to 10 volts. Okay. That's the first step. We are done with this and this, right? Well, actually, the way you're going to do it, we're done with this one. And what you're going to do now, we are going to read the voltage across the resistor. That's what I call the V1. Okay, connect the DMM between the closer end of the resistor. First, you have to reinvert the polarity, okay, and now we did the negative here, V total, disconnect everything and start all over again. Here you go. And multimeter is going to be connected between the two ends of the resistor. One end here, another end here. And then you repeat the same steps we did before. 10, 11, 12. Okay, and here you go. This column here, we're done with this column. And now we are going to do that for the light bulb, right? Invert the polarity. Let's see. Yeah, invert the polarity. Why do I have that thing here? Yeah, I shouldn't have this slide here. For some reason it's here, I don't know why. Okay, so I will erase it altogether. I don't need that. Hey, here. Disconnect everything from the multimeter and then do the same for the light bulb now. Not this one. Oh, first we do this one, right? Total for the V1. I call that the V1, and the next is the VB. That's what we're doing next. Measure the total voltage, set the power supply to different voltages, and measure. First, measure the total voltage with the multimeter, measure the voltage across the resistor, and now measure the voltage across the bulb. Okay? That's what we did. And going back here. In the next step, we are going to measure the current in the circuit, just like we did before, okay? Just like we did for, and then we start from scratch, just for practicing purpose, okay? Start from scratch, here you go. You measure the voltage, what's missing now is the current, this one here. What we're going to do? We're going to plot V against I, okay? And you're going to see that if we plot VB against I, you're going to see that this one does not obey the Ohm's law. But this one does obey the Ohm's law because it's a resistor. Okay. So go change the voltage here. And now we don't need that anymore. We're going to use the ammeter. Okay. And the ammeter. This ammeter is a funny one. Okay. It's not an actual ammeter that we have in real life. They just put. I wish they had drawn a ammeter that were more realistic. They put just like a kind of a spyglass, right, to measure the current. When in reality, he was supposed to put one end here, another end there. But and that's what they're going to do now. We go. Disconnect everything, start from scratch, power supply, digital multimeter to measure current, negative goes to the resistor to the light bulb, and we close the circuit. This ammeter will measure the current in the circuit. Vary the voltage of the power supply, and we are done with every measurement that we need to make. Those 1, 2, 3, 4, 5 columns plus those 2 cells here, they are all measurement. Everything else are just results. Okay? V1 plus VB, right? I'm summing V1 and VB. We should get it very close to the V total. And then we use Ohm's law to measure the resistance of the bulb. Okay, and you can see that the resistance of the bulb varies when we use this formula. This is exactly what happens in real life. Okay, 9, 7, 4, 2, see that? 4, 7, 9. And what you have to do next? Graph plotting. Graph plotting. Plot VB along the y-axis and I along the x-axis. And that's going to be now that you're going to see that the light bulb does not display that straight line that the resistors display. Okay? Insert, chart. Here you go. Do you see that? For comparison purposes, I'm going to plot V1 and I, just for comparison purposes, which, by the way, is for the resistor, right? This guy here is a straight line, but not this one. And if I go ahead and put the trend line for this one here, what do I get? I'm going to get the resistance of my resistor, 79.353. Let's see, 79 is 81, only 2% difference. Okay, 81 right in here, 79 right here. But the light bulb, because it's not an ohmic device, it does not display this straight line that it is displayed by resistors. You see kind of a third order polynomial here. That's how we have here is a third order polynomial. And then what you're going to do next? You're going to fit a third order polynomial trend line for a third order polynomial. What do we do? You know, oops, not this one. Here you go. Let's start again. Close it. Okay, click on the data points, right click, add trend line, and now you're going to look not for the linear, not for the logarithmic, you're going to look for the polynomial and set the order to the third power. Okay? Display equation chart, display R squared. Here you go. Here's the regression equation for the third order polynomial. X to the cube, x squared, x, and so on. Okay? Negative, positive, negative, positive. The third order, and I want to go through all of you. 11:15 right now. Let's see if everybody's in there. Sky, are you there, Sky? I'm giving you another opportunity here. Sky is not here. Huh? Yeah, she left. Okay, I'm gonna put a 0 here for Sky. And Vanessa, what do you want to do, Vanessa? Do you want to join another group since you are by yourself here in group number 2?
Sure.
Yeah, you want to do that? Are you sure? Okay. So the
Yeah.
one I suggest is join group number 3. Okay, Ashley, Zumo, and Corina. This is the group that has only 2 students there. And talk to them. And Ashley, can you please welcome Ashley and Corina? Could you please welcome Vanessa to your group? I'll put it here, group number 3, and I put a star here up to was group number 2. Was group number 2 until lab 6, right? From lab 7 became group number 3. From lab 7 became joint group Number 3. Okay, 11:15. Let's go for our break. In this meantime, try to get hold of the students, okay, Vanessa? The other 2 students, Ashley and Corina, right? Ashley and Corina. We're gonna have our break. 11:16 a.m. to 11:31 a.m. Okay, and I see you in 15 minutes. Okay. So see you. Stop sharing. Screen 2. Okay, so we are back here. Now let's see how everybody's doing. Lab 7. And let's see. Well, first thing I want to know is if you plotted the graph, right? Let's see. Let's do the following. Let's plot 2 graphs, okay? Going back here. Here you go. Plot VB along the y-axis and I along the x-axis. And then let's see. Plot V1 along the y-axis and I along the x-axis. Fit a linear curve. Fit a linear curve to this graph. Plotting. Blackjack, okay. And what we can do here, ideally, and then, you know, compare, here you go. Compare the slope of the second graph with the resistor value, right? Compare the slope of the second graph with the resistor value. Which should be very close. So let's see how we are doing here. Plot. Jacqueline, did you plot the graph? Oh, Jacqueline is not here. Let's see. Oh my goodness. Oh, she is here. Okay. Okay, good. For some reason, your name is not. Oh yeah, I see your name now. Thank you, Jack. Okay, and remember 2 graphs, right? Plot 2 graphs. Did you plot the 2 graphs or just one? Oh, both. Okay, that's good. Thank you. How does the slope of the second graph compare with the resistor value in your table? The question is for you, Jacqueline. I haven't checked on that yet. Yeah, let's do the following. Write down, let's see how we're going to do that. So you can compare it. Ideally, I should have put another table here. Yeah, that would be the ideal, but that's going to be for next semester. Okay, all I have to do is to, you know, look at the number right here. Okay, Jacqueline. You know, and here I'm having 81.12, right? And the slope that I'm getting 75.353. It's approximately 2% difference. 2 units of difference, right? It's a little bit more than, yeah, it's a little bit more than 2% of difference. Check if you get something like that. Okay. Next, Yorgo. Did you plot the two graphs, Yorgo? Is Yorgo still here? Wow, Yorgo is not here. Ah,
Professor Yorgo's internet went down. He just told us like a couple minutes ago.
okay. Okay, internet down. Internet down. Okay. So let's see, Lizelle is not here, right? And Paul Zapata. Okay, thank you, Paul. Okay, did you plot the two graphs? Okay, and how does the slope of the second graph compare with the resistor value that you measure? You can type here in the screen, in the chat.
Professor, I think I made a mistake because the slope that I have isn't similar to the one that you have. Could I see how, like, if I plotted the correct ones?
Well, yeah, it shouldn't be the same as mine, okay? Because my data is different from yours,
Yeah,
okay?
no, I'm saying the slope, it's not, I don't believe it's similar because like the slope I have for the second graph is 9.6 and it's not
9.6. Your group number
1.
one. Let's see. Now let me get your data here. Group number 1. Okay, so VB, right? I. Maybe insert. Okay, you got something like that, right? Trend line should be a polynomial of third order. Display equation chart, display R square value. Here you go. Like that. That
Okay,
you
yeah, okay. So I did get that.
okay. Now the next one. What we're asking here, where we want the V1 and I. V1 and take a look here at your 81, right? R1 is 81 ohms. Do you see that in the cell?
Yes, I do.
Okay, you are supposed to get something close to 81 as a slope. There you go. It's a straight line. Definitely add trend line display. Why is that? You're right.
Yeah, I was getting this. That's the exact same thing I got.
Strange, huh? Let's see what's going on here. Huh. I have to figure out why is that so strange. Maybe, let's see. It, huh. Yeah, that's a mystery for me. Is it possible? No, it's not possible. V1. Wow. Now I do not know what happened. All those years. 8 and I. Is it possible? Yeah, you're right. There's something wrong here in this data, okay? I do not know what is wrong with this data. So what I'm gonna do, I think it's better if I give you another data set. Okay, and yeah, you're getting, doesn't look like I did anything wrong. Let's see. Huh. 10, V1 is close to 10, VNI, but wait a minute. This current is too high. It seems to me that this current is too high. Yeah, okay, most likely, it looks like they missed on the current here. I'm gonna give you another data set, okay? And your group number 1, right?
Yes.
So let me, okay, seems wrong, something wrong. something wrong with the data, okay? I'm gonna write that down here. Try again. Going on here. Okay. Try again. Good. So, and yeah. I'm gonna give you, okay, I'm gonna make this one group one. Let's see. Let's make sure it's not the same data. Yeah, see, Paul, that current in your table was too high, one order of magnitude high. You know, maybe the students didn't measure the current properly. That's why you're getting that odd result. Okay, let's see if we plot this one, you should get things that we do not know what's happening until we get into the, let's see here, 97 here, 92 here. So we are talking about 5% difference, okay? So most likely what happened here, Paul, most likely what happened here was that they typed it incorrectly. Maybe they made to the -2, -2, -2, -2. Most likely that's what happened. Okay, the students, when they collect this data, they type it incorrectly. It's just supposed to be -2. Let's see if that's the case. If you know, if I get a good data here, then I don't need to divide by 10. Let's see. Let's see if we get a better data now if we do that. Well, I see. Oh, yeah, okay. Okay, so let's see here. Now I'm gonna add a trend line to that. I get 96, right? I get 96. This one is 81. That's a 10%, 15% difference. Yeah, maybe most likely that was not the problem. Maybe it's just something else. We're getting a 15% difference. That's too much. Yeah, definitely. Okay, so I'm gonna keep it something wrong here, and I will upload the other graph for you. It is this one here. I already plotted the graph, right? Let's do it again. 97, 97, 95, 92 is 5%, a little bit more than 5%. Okay, so let's renumber this one to group one. Okay, and I will put this one here as 04. Okay, and the other one, 04 becomes 01. And 0.1 becomes 0.4. Okay, so going back to your group number 1. So replace that spreadsheet with this new one, okay? Yes, replace. Zero 07. 11:47. That's good. 15 minutes to go. Okay, now you now you have to work on that, right? Repeat what you did so far. I'm sorry for that. Paul Zapata. So I'm gonna put here that you're working on that. Okay, Jacqueline. So you gotta do the same. Okay, Jacqueline, and tell Yorgo about that. Now Norberto is not here. Vanessa. Hello, Vanessa.
Yes, so I got my first slope is close to that first resistor value. It's at 85.2.
Okay.
And then same thing with the second one.
85.2, you said?
Yeah.
That's the slope value?
Mm-hmm.
And what's the value of the resistance?
Of the other one?
Yeah, the resistance.
Oh, the resistance
for
value
that
is
one,
98.
98. Okay, 98 is like 13%.
90.8.
90.8. Okay, so much better. 5%. We're talking about 5%. That's good. And then the other one, you got that third order.
My slope was
Phenomenal.
one.
There are two graphs, right? The first one is the
Yeah.
bulb, right?
Yes.
So you get a third order polynomial? Okay. Why it seems not coming? Okay, here you go. Third order polynomial that looks just like that. Okay.
Yes.
Okay, so this one is an ohmic element. This one is not an ohmic element. And the flashlight bulb is just one possible non-ohmic element. LEDs are non-ohmic element as well. Okay, light emitting diodes. And that is Sky. Sky is not here. Okay, was at the beginning but left, was at the beginning. But didn't answer, right? Didn't answer overall. But did not answer role and left. Okay, Ashley, your turn now, Ashley. You plot the two graphs? Hello, Ashley. Okay, good. So do you get the same result as Vanessa? Okay, good. So yes, Corina, any problems there, Corina? Do you plot the two graphs? Got the same. Okay, that's good. And one is a third order polynomial, the other is just a straight line. And what else? Now work on this units, right? Make sure you work on the units. Okay, I'm seeing at least one group, they are not filling up the units, and because of that, they are missing on the points. Okay, the units are very important. See, you need to plug in the units for the resistor of the bulb. You need to, I'm gonna highlight where you gotta put the units, right? Highlight in gray. Right in here. 1, 2, 3, 4, 5, 6, And that is only 6 units that you have to fill in. Okay. So let's see. Jacqueline, did you fill up the units? Yeah, not yet. Okay, so you're working on that. I'm gonna put it. Yorgo. Yorgo still didn't return. Okay, Lizelle is not here. Paul Zapata. Are you work? Did you finish the units, Paul? Still working. Okay. Norberto is not here. Vanessa, how are you doing with the units? Did you finish? Yeah. Okay. Good. Okay. So so start working on the significant figures, right? This Sky is not here. Ashley. Hello, Ashley. Did you work? Are you working on? Did you finish the units? Okay. So start work on the significant figures now. Have more 8 minutes to go. Corina, what about your units? You finished too. Okay, good. So internet's still down. Okay. Next one will be sigfix. 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 And what else do we have? And let's not forget CL. CL. Okay. The sigfix. Let me give you a little. Everything here, because of their numeric value, they should all be in numeric format. Okay, everything. So go ahead and change it from, scientific format to numeric. Right? Instead of scientific, put everything as a number. And the next step is to figure out how many significant digits you have to put it here. Okay? Here, definitely you have to put more decimal places here too, because those measurements are not going to be 0. Okay? So definitely, but you got to figure out how many significant figures it's going to be, right? Gotta look at that table. Gotta look at that table that I provided you. And significant figures, all of that here. Let's see. I'm going to put significant figures in yellow. Right? Yellow is the significant figures. The gray is the units. Get the table for this 1155, and then this one here is going to be, let's see which color I put. I'm gonna put it at that green color, light green. Let's put this one, orange, CL, and everything else too, right? Everything else here. I'm gonna put as orange as well. That's what you have to do for this spreadsheet. Do I have anything else here I have to show you? Yeah, we're done here. 4 minutes to 12 noon. Any questions? Okay, we can stop here now. If you don't have any questions, I'll have office hours until 12:45. If you wanna solve any, have any questions, if you have any questions, you can stay around and we'll talk. Okay, and by the way, I posted the notes, the recordings for the previous two labs. Okay, so you should be able to access the previous two labs and the previous two class meetings. Sorry, the previous two class meetings. So is there in Canvas, and I am going to upload as well the notes for today. Okay, so I see you next week. Bye bye. Welcome.